In chapter 1, we are going to be discussing with us together transformation of stress components or elements. In solid 1, we have gone through, or you have gone through developing stresses due to individual loadings, and then we come up with stress elements due to the combined loadings. Now we continue in this chapter by transforming the stresses on the stress elements in various orientation of the stress elements, whereby we will eventually be able to obtain the maximum normal stresses, or also called the principal stresses, and also the maximum shear stress for a 2D stress elements. And finally, we should be able to also find the absolute maximum shear stress at a point which might be out of plane. Now in solid 1, we have thought, for example, we have a beam-like element with loading that is in the axial direction, or in this case is the longitudinal axis. So if we only have one load in the uniaxial direction, we have covered that in solid mechanics 1. Okay. And what we do is we take a section which is perpendicular to the direction of the load, and we find the stress acting on the surface, and that is due to the internal load. So when we take a section within the material itself, we are going to develop or find the internal load P. So P in this equation is the internal load, but since there's only one external load, so it is equal to the external load. And if we divide the external load with the cross-sectional area A0, then we will get the average average normal stress. Okay. So what we then have is this normal stress, which is acting in the direction of the load in the longitudinal direction. That is what we cover in solid 1. But if we go further and look at various direction or inclination of the sectioning surface, if we take the sectioning surface with angle theta from the normal, so in this case, theta here, if that is the normal direction, right? Theta is that angle there to the inclined surface. Then we can find that the stress, the normal stress, will change due to the change in the surface area, because the surface area will change from A0. Now it's not A0 anymore. Okay, it's larger. And also we will get a component which is parallel to the surface. So that component will create shear stress. So we will have a normal stress component and a shear stress component. And the values of the normal and shear stresses will change according to the angle theta. Right? Whether we are going counterclockwise or we are going clockwise, we will have to find the values, and they all will be found using the equation given here. Sigma is equal to P over A0 cos square theta, and the shear stress is given by P over A0, that's the nominal stress, times sin theta cos theta. The maximum normal stress from those equations can be found, that is when they are perpendicular to the direction of the load. So we have the maximum stress is P over A0, while in that condition we do not have a parallel component of the load. So tau, or the shear stress, is 0. But as we shift the plane around with various values of theta, we will find that at 45 degrees from the axis, where the counterclockwise or clockwise at 45 degrees, where tau is maximum. Okay, tau is maximum when the angle theta is 45 degrees for a uniaxial loading. So if we take an element here, right? Now that element is in the axial direction. Therefore, what we then have for a 2D element, that is the x direction, okay, the longitudinal direction. We will have sigma here, which is the maximum stress, okay, maximum normal stress for this problem here. Okay, we don't have any shear stresses, but if we take an element on the inclined plane, so what we then have is we have an inclined plane theta, okay, and that is the x direction. So if we take a stress element at an incline of theta, then we are going to have a stress prime. So if that is x and that is x prime, so that is sigma x prime. Okay, so we have here sigma x prime, which is at an angle. And on this surface here, we will have a shear component, and that is tau x prime. Okay, so we have a shear component which is given by this equation here. Okay, tau is P over A naught sin theta cos theta. So we have complementary shear stress here, and also on this surface. Okay, and on top of that, because this is a slanted surface similar to this one, we will also have components of normal stresses. So we have sigma y prime, okay, sigma y prime, considering this is y prime direction and this is the y direction. Okay, so we can see that as we change the orientation of the stress element from its main direction, which is the longitudinal direction for this simple loading, we'll find that it becomes a complex stress situation where we have sigma x prime, we have sigma y prime, and we have tau x prime y prime. Okay, so that's in the x plane, but in the y direction, so it's tau xy. Okay, so we have complementary shear stress all around the stress element. So similarly, if we have a bending loading, we just have an object and we bend, just pure bending. Then we find that the strain will be distributed linearly. Similarly, the stress will be distributed linearly as well, where here is the neutral axis, right? And we know that due to bending, stress at the neutral axis is 0, maximum is at the furthest point from the neutral axis. So in this case, here, if we take a stress element here, okay, number 1, let's say that's number 1. Now, just assume that we have a positive bending moment M, therefore on top is compressive. So if we take a stress element at number 1, then we have a compressive stress. Okay? So that's the maximum bending stress for stress element number 1. There's no shear stress there, right? If we take at number 2, then we will have a tensile stress. So that's a sigma bending for number 2, sigma 2. Okay, so we have a tensile condition and compression condition. That's due to bending only. There's no shear stress in bending, only tensile or compressive normal stresses. So if you move around the element as you go down towards the neutral axis, the stress will get smaller and smaller, and at the neutral axis you don't have any more bending stresses. So if you look carefully, we take the orientation of the initial element in the direction that we know, and that direction is the longitudinal direction. So in real life, if you have, for example, this pen here, we will tend to take an element which is in the longitudinal direction because that is the known direction, and we can do analysis in that known direction in solid 1. But if we combine the loading, not just bending but also we have axial load, for example, and torsion, then this is not the maximum stress. Okay, this might not be the maximum normal stress. So we have a combination effect. Shear loading, so it's the same thing here. If it's pure shear. Now for pure shear, we know that the maximum is at the neutral axis. Okay, if we take a stress element, then number 1. So what you then have is you have stress element